Make a screencast, they say. Give us a little bit more on sigma and pi bonding and orbital hybridization. So here we go. Okay, a sigma bond, and we're working in the realm of covalent bonding here. A sigma bond is basically a single bond, or it's like the first bond of a multiple bond. So like if there's a double bond or a triple bond, at least one of those bonds is a single bond, a sigma bond, okay? So for example, in any of these kind of structures, you know, that we have the, that we have a single bond here, these are all just gonna be, you know, classic examples of a sigma bond, okay? So these are sigma bonds. What are represented in a, what's represented by the sigma bond? What does it actually mean? Well, if we just take any old structure here that has a single bond, what it represents is the direct overlap of orbitals, the direct overlap of atomic orbitals. Okay, so the idea is this thing called valence bond theory, and that basically says that when there's a covalent bond, the orbitals, the atomic orbitals of each respective atom participating in the bond are going to overlap. So for example, here for the hydrogen down at the bottom, we would have the 1s orbital of one hydrogen just overlapping with the 1s orbital of the other hydrogen, and the electrons would be somewhere in the middle, okay? And so this idea is what's behind the idea of a sigma bond. If you look at the CH bond there, yeah, it could be the p orbital of carbon and the s orbital of hydrogen, whatever. But the idea is that in a sigma bond, it's this direct overlap, first of all, and the electrons are directly between the two nuclei of the two atoms involved, okay? The electrons are directly between the nuclei, okay? Or at least they're somewhere on the plane between those two nuclei. They won't be like evenly in the middle unless it's like a totally non-polar bond like in hydrogen. All right, contrast that sigma bonding with what we call pi bonding. In pi bonding, these are always going to be like the second bond of a double bond or the second and third bond of a triple bond. So let's take a structure like this. Basically, if this guy here in the middle is your standard sigma bond like we talked about, these two on the outside are both going to be pi bonds. Okay, so there's a pi bond there, and there's a pi bond there. And then back out here, these two carbon-hydrogen bonds, these are also just sigma bonds, okay? So what's going on with a pi bond? Well, in a pi bond, they're always created between parallel p orbitals. So if you look at for example, what's left in terms of the valence bond theory, we would have to have the p orbital from one of the bonding atoms and the p orbital, the parallel p orbital from another bonding atom, and then where the electrons would actually be would be above and below the plane between the two nuclei. Okay, so the nuclei, I'm going to put a big thick dot where the nuclei would be. Okay, this is where the electrons would actually be located in any given pi bond. Okay, so this would represent one pi bond, everything I've drawn in this picture right here. Okay, if you had a second pi bond, well, then you would have to have a second set of parallel p orbitals. So maybe now it's the ones like coming out of the plane and going into the plane. I don't draw them very well, but imagine these ones are actually coming out of the page and going into the page. And so where the electron density is in that bond, and again, this contrasts with a sigma bond, but where the electrons are here is in this area towards us out of the page and into the page. Okay, so they are not along the, notice that electrons are not along the plane between the two nuclei. They're above and below, or in front of and behind the plane between the two nuclei in a pi bond. So I can write that on there. Electrons in a pi bond are above and below the plane between the two nuclei. Worth noting, as an add-on for pi bonds, all delocalized electrons are always pi bonding electrons. So all delocalized electrons are pi bonding electrons. So if you imagine the electrons that are shared in the ring structure of benzene, or the electron pair that is shared between the two locations in ozone, okay, if we just quickly draw an ozone, and hopefully I don't make a mistake on it. You know, remember, this electron pair can be over here, or it can possibly be over here, and actually kind of exists in both places as this like 1.5, 1.5 bond type thing. Well, these are delocalized electrons, and where they'd be delocalized between is kind of between the parallel p orbitals of the three oxygen atoms that make up ozone. All right, let's talk hybridization. So hybridization is just saying that if we accept the valence bond theory that orbitals are going to have to overlap when a covalent bond is created, then we have some issues with in a couple of areas if we just accept the standard overlapping of atomic orbitals like s orbitals and p orbitals and stuff like that. And the issues we have, and so I'll say that hybridization solves issues. It solves issues of geometry, which I'll explain, and it kind of solves issues of energetics. And what it does is it makes all the bonds that a central atom participates in degenerate. It makes them equal in energy, and it also allows for the proper geometries that we observe in molecules rather than what should be dictated by the relative positions of standard atomic orbitals. So let's take, for the example, CH4. Let's look at methane, CH4, okay? Well, if we examine the classic orbitals that we imagine in a carbon atom, okay, let's take a look at where its valence electrons are. We would have in the 2s sublevel and in the 2p sublevel, and subsequent 3 orbitals, we would have 4 valence electrons like this, right? So if carbon's going to make 4 bonds, like how does that all work? Well, there's its 4 electrons. What's it going to do? Is it going to have like 2 of these? Is it going to have this orbital overlapping twice with hydrogens 1s, with a couple of hydrogens 1s orbitals? Like, is that what's going to happen? And then the other 1s hydrogens are going to overlap with these, and then there's like a blank one. Like, what is this? What is this mess, right? So I'll explain what actually happens and how hybridization helps it. Okay, so what actually happens, or the kind of construct that we put on this to rationalize what happens, is in the valence of, again, we're focusing on trying to teach me how to spell. In the valence of carbon, okay, we have the 2s and we have the 2p, and there we go, they're like that. Well, what actually happens is the hybridization phenomenon, and what that means is like these four. I gotta be a little bit careful how I draw this. I don't want to give you a misconception here, but these four former atomic orbitals end up creating four new orbitals, and we call those four new orbitals sp3 orbitals. That naming is because they are the former s and three separate p atomic orbitals, and then each one of those is the same in energy. Okay, so each one gets one electron of those four electrons, and then that way each one of those four can make a nice even energy bond with the four respective hydrogens. Okay, so then you can have a hydrogen with its s with its s orbital electron. You can have it bonding in each one of those positions, and each one of those bonds is going to be the same. Okay, so it solves that energy issue. The second thing it enables is that if we had to bond like p orbitals, okay, if we had to take these imagine hybridization didn't happen. If we had to bond those p orbitals, what's the orientation of p orbitals in a carbon atom, or indeed in any atom? You probably remember one is on the y-axis and one is on the x-axis, and one is on like the z-axis, so it would be coming right at us. But the deal is, if those are equally on those axes, then the angle between those p orbitals is actually 90 degrees, isn't it? And we can't have bonding between 90-degree orbitals here, if we look back up at the Lewis structure, because then these bond angles would be 90 degrees. But we don't observe 90-degree bond angles in the structure, okay? So they can't be. What we actually observe is 109.5 degree bond angles. And so with the sp3 orbital hybridization, we can actually have those these new funny little orbitals created that will allow for that interesting 109.5 geometry. I'm going to draw it in a kind of weird way, but it'll end up forming that proper tetrahedral structure where the bond angle becomes 109.5 degrees. Okay, there's not enough flexibility in the classic p orbital orientation to enable that. All right, so recognizing hybridization, if you have an sp hybrid central atom, that means it's a combo of an s, of a former s, and a former p. Okay, in this case, an sp hybrid would have two electron groups, or sometimes you hear instructors call this electron domains, whatever. It would have two electron groups around the central atom. A central atom with two electron groups is always sp hybridized. Okay, so for example, we had, even if we have a little one that has the incomplete octet, like, BeF2, what is that, beryllium fluoride? Beryllium fluoride, we would draw like this. It's kind of a strange incomplete valence or whatever. But for sure, if there's two electron groups around it, we would say that the Be is sp hybridized. It's sp hybridized. If we had a carbon can do all different hybridizations, which is why we talk about it so much. One of the many reasons, but in this case, you can also see that around that central carbon, it's got 1, 2 electron groups. Doesn't matter that they're single, double, triple bonds, or whatever they are. If it has 2 groups around it, it's an sp hybridized thing. And then if you remember, this hopefully makes a little bit of sense, because if you remember where its valence electrons are, okay, remember we said it was like this. Well, we're going to combine 2 of those old orbitals. We're going to combine an s and a p, and these are going to be the sp hybrids. And then what's left over is we still have a couple of a couple of empty 2p orbitals, don't we? Well, guess what those empty 2p orbitals are going to do? Those are going to be the source of the pi bonds over here, because we said pi bonds have to happen between parallel p orbitals on the adjacent atoms. So you got two of these that can do pi bonds, and you got two of those sps that can do the sigma bonds. And isn't it just a wonderful world? Let's keep on rocking through all the examples here. So let's look at a few others. Here's NH3. We look at him a lot. That's ammonia. Oh, what a botched job I did trying to draw that thing. Yikes. Okay. Here's a generally properly drawn ammonia. What's the hybridization? Well, there's 1, 2, 3, 4 electron groups around it. Yes, that's right. A lone pair counts as an electron group. So that nitrogen is going to be sp3 hybridized. Okay? And we could draw the orbital diagrams and rationalize the whole thing, but believe me, let's take BF3, another little incomplete octet. What's the hybridization there? Well, because it has 1, 2, 3 electron groups around it, that's what we call an sp2. Okay? How about a carbon that does it? Why not? Here's a carbon molecule, or a carbon-based molecule. I don't know what it is. Ethine, actually, this would be called. Ethine. Let me fill out the hydrogens so as to not confuse. Let's focus on this carbon right here. Oh, we have a problem. I put too many hydrogens on here. There we go. I'm gonna get my act together here. Oh, whatever. Okay. What's the hybridization of that carbon? That's got to be sp2, because it has 1, 2, 3 electron groups around it, so that's an sp2. How about this guy over here? What about him? Well, 1, 2, 3. He's an sp2 as well. Have another one. Oh, we already looked at this one, I think. Well, anyways, it's sp. Both of these are sp, because they only have 1, 2 electron groups around each respective carbon. 1, 2. So they're sp hybrids.